So I have to shout. Great. Fantastic. I much prefer to project. So it's great to be back in Oregon. I was here, I think, 7 years ago, and I have not been back to Eugene. I have a 3-year-old daughter who insists that when I travel, I bring an animal in case I miss her, and she gave me this duck, which I thought was appropriate. Totally uncoordinated. So we have a duck. I feel a little bit like the sort of light after-dinner entertainment after all the amazing type 3 you guys have done. But I'm going to tell you about an area that I think is really exciting. At least I also appreciate theoretical aspects of PL, but I've been spending most of my time over the last few years working on networking problems. So I hope I'll convince some of you that there's some meat here, and that's a good area to work in. If nothing else, you can also learn how to fix your Wi-Fi when you go home for Thanksgiving. So as motivation, a lot of the languages that we use today, so languages like C, Java, Python, OCaml, Haskell, they were designed in an era where computers look like this. This is, I think, actually the computer that I learned how to program on. It's a Sun, and the machines in my undergrad at the time were Sun workstations. But if you talk to people at large tech companies, the way they think about computation is like this. So engineers at Google, Facebook, Microsoft, they write computations that run on thousands of machines all the time. And it's very different to write an application that runs on a single kind of slow Sun workstation versus writing a program that's going to run in the cloud. And even if you're not using tens of thousands of machines, sort of the very nature of applications is pretty different today. So I use services like GitHub and Gmail and YouTube all the time. And rather than running some local application on my laptop or my phone, most of the computation's happening up in the cloud somewhere, and then my machine is running some residual computation and communicating back and forth. So in these sort of two different paradigms, the sort of old school paradigm, it's not that we didn't have to deal with networks or distribution or so on, but for the most part, our languages are designed for programming sort of one standalone machine. Most of the computation you can think of as being sort of centralized on that machine. There are exceptions, but most languages tend to excel most at sort of expressing sequential computation. And the way that we reason about correctness is things like relational parametricity, which is sort of capturing functional properties of programs. So in this other more modern paradigm, all of these characteristics of computation completely change. So instead of being standalone, now all of the devices are networked. Instead of things being centralized, your different computation nodes, where data is stored, it's all distributed. Because of the way the system is structured, the computation is necessarily concurrent. And the way we think about correctness is we think about functional correctness, but then we also think about all the different ways that the components of the system can interact. And so if we want to apply the same level of elegance and rigor that we have for languages like Haskell and OCaml and standard ML and so on, I think we need new kinds of abstractions and compilers and type checkers and tools for programming these network systems. Okay, so another way to look at it is, we're sort of going from, a single node to suddenly trying to think about how we program this kind of mess. And the reason that you might care about the network in particular is that, the network plays this critical role. It's what sits between all the different nodes. And if you want to sort of run a complex computation on that kind of machine, you need to be able to specify, how these nodes should be able to communicate. Is communication going to be point-to-point? Is it going to be broadcast? Are there going to be different, levels of service or different kinds of communication that the network provides? Performance will also be very important. When you have all of the components of a computation sort of tightly bundled on one machine, of course, there's different costs, like doing things on the chip versus the memory. There's a difference there, but those differences really become important when you're talking about computations that are running across a data center or even around the world. And so the network can play a key role in sort of masking some of those differences and providing good performance. And then the other reason that I think thinking about applying programming language ideas to networks is exciting is networks are often sort of the first line of defense when you think about attacks and security. And if you have a network that can provide to you sort of provable isolation, so we know that this part of the network cannot talk to this part of the network, then we can use that as a basis for starting to prove that our systems are secure. Okay, so this is why I think we should be interested in applying programming language techniques to networks. The reason we should do it now is that there's a really exciting trend in industry that has been going on for about the last 5 years that gives us sort of the underlying machines and technology we need to apply language techniques to them. So if I had to sort of describe what this trend is, let me go back and tell a little bit of history. So if you rewind to, say, the 1960s, you bought a computer, it was something like this, a big mainframe that you might buy from a vendor like IBM. And IBM would sell you, the chips that were in that machine, all of the peripherals, the case. They'd also sell you the operating system. So you couldn't, erase your hard drive and install Linux. Didn't exist. You had to run IBM's operating system. They'd sell you all the applications that ran on that. And it was actually difficult to impossible for sort of mere mortal programmers to figure out how to write new applications on these kinds of machines. And the whole thing was kind of closed and tightly coupled together. And over the last 30, 40 years, we've moved to this different setting. This is one of the Facebook Open Compute project nodes, where we've kind of completely opened up and commoditized all of the components that we use to build computations. So, x86 is sort of the standard for, laptops and servers. On phones, we have different kinds of chips. But all of these things have well-documented low-level machine languages, operating system abstractions, language abstractions that sit on top. And all of the, rich computing system we're building today sort of exploit all that openness and standardization to enable all kinds of innovation. So if you look in networking, let's rewind to sort of the start of the internet. This is Leonard Kleinrock, who was at UCLA, who was one of the first people who was involved with building the internet. And that was one of the first internet routers, a so-called IMP node. It looks a lot like the IBM 360. It's kind of this big, refrigerator-sized thing. And a lot of early networking gear was sort of big and monolithic in the same way that mainframe computers were. So if you fast forward to the early 2000s, say 2009, or 2008 or 2009, this is sort of the state of the art for a big router on the internet. And you'll notice that it, too, looks kind of like a mainframe. It's a Cisco box. It's got a bunch of custom chips inside. It's got a custom operating system that Cisco sells you. It's got a bunch of applications that Cisco sells you. So networking, there's lots of things that happen in going from here to here. This thing is really, really fast. It can process a lot of traffic. But it doesn't have the same kind of open structure that we have in standard computing. So what started to happen over the last 5 years is people have realized that this mainframe way of doing things is not the best, and it's actually slowing us down. And so there's been a big effort to try to do the same kind of evolution or revolution as happened in computing in networking. So this is another Facebook Open Compute project node. It's their network switch. And just like a standard commodity server, this thing has standard functionality. It's clearly documented. It has a low-level machine language that you can read and go program. So I think this is really exciting because sort of right now, there's a chance to apply all of the techniques that we've been developing in PL over the last 30 or 40 years to these problems. So we can formalize the behavior of these devices precisely using operational semantics, denotational semantics, axiomatic semantics. We can develop sort of richer theories that capture sort of idioms about how lots of programs that run on those devices work. So if we want to reason about various kinds of security properties, there might be some rich kind of theory that we can develop that will tell us how to ensure security by construction. There's also it's sort of another instance of the full employment theorem for compiler writers, because we sort of have to rethink the entire hardware software stack and sort of build up the ecosystem that we have for computing in the domain of networking. Okay, so I think this is really exciting, and it's what I've been spending almost all my time over the last 6 years working on. So my plan for these lectures are to tell you a bit about this work. And don't be fooled from my introduction. This is not going to be a flashy technical-free talk. We'll get to denotational models, equational reasoning, soundness and completeness, a beautiful connection to automata theory. I'm still working on my last day slides. We may get to some probabilistic semantics as well, if I have time. But to get there, I have to tell you to sort of lay the foundation. So I'm going to cover a bunch of sort of undergrad level networking stuff today so that we can understand what these machines are and what languages for them might look like. So I'll start by giving you a sort of, I hope, 10-minute crash course in networking. Actually, just out of curiosity, how many of you have taken an undergrad networking class? Okay, that's about what I expected, maybe 2/3 of you. So much of this will be old hat, but I think there'll be, even for those of you who've taken a class, a few things you've missed. I'll also tell you about this new kind of architecture that's being developed. It's called software-defined networking. And then today I'll close by giving you a small taste of sort of how we can apply rigorous programming language techniques to this domain by showing you a language called featherweight OpenFlow that my PhD student Mark Reitblatt, Arjun Guha at UMass, and myself developed a few years ago. So we'll see an example of what operational semantics looks like in this setting. Tomorrow, we'll kind of lift off from networking and get into language design. So I'm going to tell you about a family of languages that we've been working on for the last 3 years that is based on essentially automata theory. To be a little more precise, it's a system called clean algebra with tests that my colleague Dexter Cozen's been working on for about 20 years. So I'll motivate why clean algebra with tests is a great fit for networks. We'll define the semantics of the language precisely, and we'll do a bunch of programming examples using it. And then I have 2 lectures tomorrow. So in the evening lecture, I'll show you one of the sort of exciting application areas of PL technology and networking that has actually gotten a ton of attention both from the systems community and in industry, and that's formal reasoning. So network operators today, the people who are in charge of running networks for campuses, large companies, and so on, they don't have things like type systems or even sort of weaker tools like testing tools. And so one of the things that they're really excited about with this kind of language approach to networking is that you could start to build those kinds of automated tools. You know, if you could type check all your router configurations, you could rule out certain bugs from ever happening. And we're starting to see tools that can do that kind of thing. So I'll show you a couple of the tools we've built for our language based on clean algebra with tests, and I'll show you an axiomatic model, the connection to automata theory in a little more detail, and how we can actually decide equivalence for programs in this language, which provides a basis for doing verification. And then on the last day, I'll tell you about some interesting implementation work we've been doing. So both how we compile these languages down to machine code for network routers and switches, how we deal with dynamic changes. So one thing that's really important in a network is that they're not static. Things like failures or policy changes, you know, a new program that arrives happen all the time. And so it's important to be able to not just program sort of the idealized situation where the network is sort of doing one thing and doing that thing perfectly. You also have to handle cases where something changes and you have to react to it. But you don't want to throw out the baby with the bathwater. So how you can build essentially runtime systems that provide nice guarantees even in the presence of these changes. And then, as I said, if there's time, I'll tell you about some ongoing work, and I'm hoping I'll have time to tell you about our most recent work on doing probabilistic programming in the context of networks. Okay, so let me start with my undergrad networking course in 10 minutes. Start the clock, so I have to finish by 11. So if you have a sort of naive view of networking, I don't know, maybe some of you are browsing Facebook right now or something, you know, you have your host sitting on one side, and you probably know that you know, there's something that connects these hosts here at Oregon. So there's some wireless access points, and then there's a campus network that probably has a bunch of Ethernet switches that provide connectivity to hosts within the U of O campus. So any host on campus can talk to any other host, or most hosts can talk to most other hosts. On the other side, you have, you know, the Facebook servers, which are probably sitting in a data center up in Bend. That's actually I think that's where that picture that I took came from. And likewise, in the data center in Bend, you have a bunch of devices. In this case, they use routers, which are a lot like switches, but they work on different aspects of the packets that they're processing. And this provides connectivity to all the machines within the data centers. Then you might have some other kinds of devices. So this is something you might not have seen if you've just taken an undergrad networking course. In order to provide sort of very good performance, most cloud applications are highly replicated. So your data at Facebook or a particular YouTube video that you want to watch or an Olympic video will actually be stored on lots and lots of machines. And what happens is when you make some request in your browser to go get that content, your content gets routed to some data center, and then sort of at the front door of that data center, there's a device called a load balancer that will essentially flip a coin and decide which backend server to route you to. So it's kind of like a router, but it's a little different. And then, of course, to bridge between the data center and the rest of the world, you need something called a gateway. Of course, there's other ISPs. So how do you get from Oregon to Facebook? Facebook actually probably peers with Oregon because they're such a big content provider. But if you were somewhere else, they might have to route through some other network like AT&T or Level 3 or any of the large ISPs. And so you need routers that run something called BGP. This is a different protocol that controls how paths work on the internet. And then you probably want things like firewalls because you want to block traffic that comes from untrustworthy networks. Oh, there's also wireless. So we need wireless access points. If you're a phone carrier, you need to provide what's called lawful intercept, meaning giving data to the NSA. So you have all these boxes that are involved in actually just getting your traffic from your laptop to a big content provider. And each color here represents a different kind of device that runs different protocols, uses different algorithms, and somehow in this kind of crazy Rube Goldberg machine, they're all kind of slapped together and actually work pretty well. Okay, so let me give you a little more detail. Let's think about Bob. I was hoping Bob would be here, but I guess he's not. So Bob and I are both big cycling fans, and we're also both PL researchers. And this is a huge problem for us because in early July, the biggest bike race starts, and the biggest conference has its deadline. So it's always this tension, like, am I going to work on my popple paper, or am I going to wake up and watch the end of the tour? So let's say one morning, Bob wakes up, he's like, my lectures are done on OPLSS, my popple submission's in good shape, let's see what's going on with the tour. So he fires up his laptop, and, well, in this case, it's hard to watch the tour in the US, so he might go find some dodgy server in Europe that has a Eurosport feed so he can watch the tour. And he's got some connection to that server over the internet, and there's a video that a streaming video that he starts watching. So the first thing that you probably know is that the experience you have is sort of that the video sort of arrives at your machine and just starts flowing. But actually, what happens is that the data in that video is actually chopped up into little chunks, little sequences of bits called packets. And the packets are what actually flows through the network. So what is a packet? So a packet is just basically a blob of bits. But those bits have some structure. And there's different kinds of packets that have different kinds of structure. I'm not going to go through all the details of this, but there's a sort of classic, if you took a networking course, this will be familiar. Most networking courses, by the way, this is being videoed, so I have to be careful what I say, but a little bit boring because you spend a lot of time sort of memorizing details about IETF standards and the OSI model and all of this. I'm not going to make you do that. But the thing to notice is that sort of the bits have structure, and different bits are interpreted as meaning different things. So a single packet is sort of this nested sort of Russian doll of bits, and at the lowest level, you have things that have to do with how those bits are encoded on the wire. So am I using an Ethernet jack? Am I using a radio that goes to some wireless access point? Something else? And then above that, you have different kinds of protocols. So Ethernet, for example, which provides connectivity to a bunch of local hosts and has its own notion of what is an address, and it uses different routing protocols to get things between local hosts. Above that, you have the so-called network layer, where you have protocols like IP addresses. This lets you send packets to any device in the world. You've got TCP above that, and then all the application data and other stuff. Okay, so the details won't be too important for this talk, but I just want you to think about a packet as essentially being a kind of record. And if you actually formalize this in type theory, which I'll show you at the end we did, it ends up being a kind of crazy dependent record because you have funny dependencies between these different layers. But for today, we'll just pretend it's a sort of record with fields that map to bits. So we'll have things like the Ethernet source and destination address, maybe the type of Ethernet packet it is, maybe something called a VLAN, and then IP, and then beyond. Okay, so the first thing I want to show you is the simplest possible device. This device really does nothing interesting. It doesn't even look at the bits in the packet. It just sort of behaves like a big wire, or a big wire with a bunch of ports. And you might buy these things if you go to Best Buy and you have $10 in your pocket. You can buy like a repeater hub with 4 ports, and all it does is if you plug in 4 Ethernet cords to that thing, any packets that arrive at any of those ports get sent to all other ports. So if Bob wants to send a message to Dan, he would put his packet out on the wire, and then the packet would actually be sent both to Dan and Zaina. So this is very simple. It doesn't require any kind of routing protocol. It doesn't require really doing any packet processing. It's just this sort of device that does a simple form of broadcast. So I'm going to call this sort of flooding. It just has this flooding behavior. Can anyone tell me what's a problem with this kind of device? Why is the internet not made of hubs? Pretty chatty, yeah. So if the internet was a hub and you received every packet sent anywhere on the internet, you'd be DDoSed all the time. You'd get all these packets arriving at your host. In fact, even probably in this room, if we had a hub, we would be pretty unhappy. Well, I might be happy because you guys wouldn't be watching videos, but you would be unhappy because your videos would be stalling and rebuffering. So there's a fancier kind of device called a switch that has some of the nice features of a hub, but it provides much better performance. So the nice features of a switch that's the same as a hub is that it's basically plug and play. So you don't need to run any kind of routing protocol. You don't need to coordinate on who is who. You just plug in some devices, and they start being able to connect to each other. And the way a switch works is it starts out by behaving like a hub. So if Bob sends a packet to Dan again, the first packet will get broadcast to both Dan and Zaina, so basically every other port besides Bob's port, because Bob doesn't know where Dan is. So the switch will just say, if I don't know where some destination is, I'm just going to flood the packet. But it has a little data structure, a little table, and what it does is it passively sort of records all of the senders and their identities, and these would actually be 48-bit numbers, but I'll just write Bob for Bob's address. And then it remembers what port was Bob connected to. So now, if Dan sends a reply, the same thing will happen. The same thing will not happen. So now, when Dan sends a reply, now the switch knows where Bob is. So assuming this packet is addressed to Bob, I'm not going to show the addresses in any of these examples, the packet can just go straight to Bob. No need to flood it. And the switch can remember, oh, Dan was on port 2. Zaina hasn't sent anything, so we don't know where she is. If she sends traffic or traffic is sent to her, we'll have to broadcast it. But you see that the reply from Dan to Bob just went directly because we knew where Bob was and we remember where Dan is. So there's really 2 things going on here. First, the learning switch, it has this table and it's always learning the locations of the hosts in the network. So just passively sort of snooping on all traffic and saying, oh, Dan was here, Bob was here, Zaina was here. And then it forwards in 2 modes. When it doesn't know where a host is, it floods. That's bad, but if some hosts are communicating, you're going to learn where they are pretty quickly. And as soon as you know where the hosts are, then you can stop flooding and do point-to-point communication.
Probably don't want to say exactly what the addresses are, but are they IP addresses?
These are MAC addresses or Ethernet addresses, yeah. And there's, if you're doing it literally in this room, there's another protocol called ARP that maps between IP addresses and MAC addresses. And that's a whole, I'm not going to talk about that, but there's a way of handling that.
Is there a port on the level of MAC address? Is there a port, a notion of a port?
No. So what this table is recording is it's recording the association between MAC addresses and ports. So the forwarding is happening out ports, but the packets have addresses that are MAC addresses. So we're basically doing a lookup of the address and then forwarding out the next hop to that host. And this actually works, I've shown it here for 1 switch, but this would work if we had a lot of switches. We'd have to be a little bit careful about the flooding, that we don't flood in a cycle, but there are also ways of dealing with that, something called spanning tree. I won't talk about that today. But this sort of simple logic extends to multiple switches as well.
Sorry, that's a stupid question, but
No, questions are great. Yeah, so if you change port, you have to be a little careful. And so this simple informal description doesn't capture it. I'll show you some code. I'm trying to remember if the code that handles it. Actually, the code also does not handle it. If you want to handle mobility, then you need to be a little bit careful, and you need to know that if you ever see a packet that was previously at some port but changed which port it's at, then you should delete the entry in your table or at least update it with the new entry. Okay, let's do another of these devices, a so-called firewall. So a firewall is a little less interesting. It's usually not doing routing. It's just sort of connecting two segments of the network. So I'm assuming that Dan, Bob, and Zaina are all connected to one port on the left, and then the internet is on the right, and we don't trust the internet. And we have a little policy which says that if the destination is ever Bob, then we want to allow the traffic to go through. We'll just pass it to the left. But if the destination is Dan, maybe we think Dan's machine's been compromised. He's been suspected of doing something crazy. So we decide to deny him for his own benefit. And Zaina, we're not sure if she's been compromised or not, so we're going to log all traffic going to her, and then someone can offline go and look at it. So what a firewall does is it basically implements that logic. So packets that come in going to Bob just flow through the firewall. They're allowed to go through, so they just go. Packets going to Dan get blocked. And packets going to Zaina get forwarded, but also logged somewhere. And then you can go do offline analysis and decide if there's something suspicious going on. Okay, so that's a firewall, nothing too fancy. The reason I'm showing you all of this is that the logic is similar but subtly different to a switch or a hub. But we have the same kind of thing going on, right? There's these nodes. We call it a different name depending on what it does. But it basically looks up, it sort of matches on packets as they come in. And then it takes various kinds of actions. And those actions can be forwarding or allow deny log, or so on. I didn't really, I'm going to be a little fast and loose in these slides. I'm trying to show different functionality. I haven't said that these are IP addresses. I've just said that the destination was Dan. So I might also match on the source if I had a notion of address. And you could do this. Firewalls can work at different levels of the packet. But okay, let's move on to something a little less trivial and look at a router. And I'm sorry, I have router twice in my slides. So a router traditionally, since we're getting into this, routes on IP addresses. And it's a little different than the previous examples I've showed you because it doesn't, the devices don't sort of operate independently. The devices actually have to run, they have to communicate themselves in order to figure out where to send traffic. And I've shown that here because I have this little diamond topology. So there's lots of paths, well, at least two non-cycle-free paths, but there's more than one path between every pair of Dan, Bob, and Zaina. So the way a router works is the forwarding is similar to the sort of non-flooding case of a switch. So we have a table on each router. I'm just going to show the leftmost router that's connected to Bob, where we keep track of addresses that we know about, so addresses that we've heard about in the network, which port you should forward to get towards those addresses. And in this example, I'm going to do a simple distance calculation to try to get the lowest distance or lowest cost paths going to those destinations. So we might start out with a router that's configured like this. So basically, this router that Bob's connected to knows nothing about anyone else. It only knows how to send packets to Bob. It knows they go out port 1, and they know that Bob is directly connected to port 1. What a router does, though, is it runs a protocol where periodically each of the routers will actually send each other messages. And I'm going to draw these packets. It's a little faint, but they're pink if you can see the color to distinguish them from the data packets. So here, the upper router might decide to, it has its own table, and it might decide to send Bob's router a message, and it says, I can reach Zaina in 1 hop and Dan in 2 hops. So assume that it already knows about the 2 paths that go clockwise around the cycle. So Bob's router can then receive this message and incorporate that information into its table. So it might decide, hey, I didn't know how to reach Dan and Zaina before, now I do. I'm going to go towards the router that sent me the message, out port 2, and I'll keep track of the distances. It's the distances that the router at port 2 told me, plus one more, because I have to go across another link. OK, so now, if Bob sends a message to Dan, we can get there, and it's going to go all the way on the long path around them. Now, of course, the router that Dan connected to might also send one of these routing messages. So it might send a message to Bob's router and say, hey, I can reach Zaina in 1 hop and Dan in 0 hops. And so Bob's router could then incorporate this information, update the ports that are the next hop towards those destinations, update the distances, and now if it sends a message to Dan, it'll just go on the short path.
I might have missed this, but how do routers know where to send the routing messages?
Say it again?
How do routers know where to send the routing messages?
So I should repeat the questions for the video. I'm sorry that I haven't been doing that. How do the routers know where to send the routing messages? Usually they're just talking to their neighbors, but let me just say there are many routing protocols out there, and they work differently. So this is a particular simple one that I'm using for the purposes of an example to show the main functionality, but these kinds of questions vary by, are you doing BGP or OSPF or ISIS? But usually you need to know where your neighbors are. OK, so a router forwards packets using tables that are computed and maintained by one of these distributed routing protocols. OK, and I've blown through my 10-minute budget, so I'm going to quickly wrap up. There's lots of other kinds of devices. There's gateways that are kind of like a switch and a router. There's network address translators. This is probably what you have at home. So this lets a bunch of addresses share one or a smaller set of IP addresses, and they multiplex outgoing traffic and have to demultiplex incoming traffic in clever ways. There's these load balancers that are used in data centers. There's intrusion detection devices. A lot of hospitals use these, also some universities, so they basically log all of the packets that come through, and then they can do offline analysis to detect for malicious content. There's things called wide area network optimizers. These are things that do various kinds of encoding tricks or caching tricks. There's also content caches. So these basically try to save from sending traffic over the wide area network whenever possible if there's a cheaper way to do that communication. OK, and the key thing to notice is that each of these different kinds of boxes, it's not like you can go buy, well, if you buy a sort of high-performance networking device, each of these is a different kind of device. You pay a different amount of money for it. You probably buy it from a different vendor. You program it in different ways. And it sort of does one fixed thing. So this is sort of the state of networking still today, but especially as of 5 years ago. OK, so what is software-defined networking? So the idea in software-defined networking is it's a clean slate architecture. So it's an attempt to sort of not try to be incrementally sort of deployable. We're going to just sort of try to think what's the best way to architect a network. And it's based on 2 key ideas. So one is that all these different kinds of network devices that do different things, there's no fundamental reason they should be different. There are some things that are special to a network device. They have to process lots of packets very quickly. So you can't, you wouldn't want to use an Intel CPU for that. Well, I shouldn't say that. Intel would like for you to use an Intel CPU to do that. But many people think that you should have a custom circuit to do that. But why does it matter if you're matching on the MAC address bits or the IP bits? I mean, they're at different offsets in the packet, and you might have to do some parsing to figure out where they are. But at the end of the day, it's just a match on some bits. So software-defined networking tries to sort of blur all these distinctions and say, we're going to be doing matching on bits and packets and then simple forms of actions that manipulate the packet. But we're not going to care so much, do we have a firewall or a router or a gateway or a load balancer? We're all just going to call them, just devices. And then the second idea is that rather than having this mishmash of algorithms and programs that are configuring those tables that are on each of the devices, we're going to actually separate what's called the data plane from the control plane. So the data plane is basically the device itself. It has a bunch of ports. They're connected to each other. They have a table. It runs a simple sort of low-level programming language that can implement various kinds of packet processing. And the control plane is the thing that runs things like routing protocols. And on most routers, for example, the control plane is actually implemented with a standard CPU running a standard operating system. The routing protocols are written in languages like C. So there's no reason that you shouldn't be able to program them. But in conventional architectures, you can't because the interfaces are not well defined. You might void your warranty if you do it, et cetera, et cetera. So the idea in software networking is let's just use a standard server to implement all of that control functionality. And let's let people write their control programs in C or Haskell or Python or whatever they want. And let's define standard interfaces for mapping between the control plane or controller running on a standard server and these generalized devices that implement forwarding. Okay, so in a little more detail, a software-defined networking architecture has two kinds of devices. You have, I'm going to call them switches, but they're not going to be like Ethernet switches or learning switches. I'll just call them switches because that's kind of the term that's come to be used for a generic packet processing element. So you have switches that expose some of this sort of general interface to programming their forwarding tables. And there are various standards people have proposed. We'll talk about one called OpenFlow today, but there's lots of others. And you can buy these switches now from most of the big hardware vendors, Dell, NEC, HP, even Cisco. And then there's another box, the red box, which is the controller. And the controller is going to have all of the smarts, all the brains, and it's going to be responsible for sort of monitoring what's going on in the network and then deciding how to configure or program the switches to implement the functionality we want. And there are standard APIs for doing that configuration. So the idea is that you could buy a switch from Dell or from NEC or from HP, and you could use the same low-level language to configure them, just like you can buy a box from AMD or Intel, and they both speak x86. And if you want to customize the network to do something new, you don't need to go buy different appliances. You can just change the program that's running upstairs. Okay, so let me go through what's in these things in a little more detail. So, and I'll focus on OpenFlow. Again, this is not the only SDN architecture out there, but it's the first one and the one that got a lot of traction. So an OpenFlow switch, think of it just as a generalized packet processing device. And its key data structure is it has one or more tables that can implement a very, very simple kind of programming language. So what these tables can do is they can match on some of the bits in the packet. Here I'm matching on IP addresses. And they can take actions like dropping the packet, forwarding out a port. They can also modify bits in the packet. And they can also, by the way, send packets to the controller if they want to. And they also have a little bit of state. I won't focus too much on state in any of my lectures, but the switches do have the ability, for example, to count how many packets matched each rule. And that's often useful for different kinds of monitoring applications. Okay, so just think of a switch as basically having a flow table or a forwarding table. I'll use those two terms interchangeably. And that forwarding table determines how the thing processes packets. The controller runs, again, a general purpose program written in a general purpose language. And basically what it does is runs a little event loop. So it has to know how to handle any of the messages that might be sent to it from one of the switches in the network. And those messages include things like when a switch connects to the network for the first time, it sends a message to the controller and says, hey, I'm here and this is my ID. So the controller might choose to use that information to do something. Likewise, if the connection between a switch and a controller is broken, then there's kind of a clean shutdown where the switch would say, hey, I'm about to disconnect. And the controller could know that that switch is about to disappear. There's similar messages for different kinds of changes to the topology of the network. So the links between switches can go up and down. If you plug in a cable, pull out a cable, there can be unexpected faults. So there's a message called port status, where a switch can notify the controller that something's changed about one of its links. And then there's a couple of sort of messages that actually carry data. One is called packet in. So a switch can choose to send some packets up to the controller. And when it does, it encapsulates the packet in this packet in message and then sends it to the controller, which can look at the packet and all of the bits and the headers and optionally even some of the payload and decide what to do. And then also, because the switches have these counters, they can send information about those counters to the controller, which could use that to maybe change which paths are used if one path is being overloaded.
Can the switches look at the counters in their rules or get forward with them?
So the question is, can the switches look at the counters in their rules? In OpenFlow, no, but there's some extensions or newer OpenFlow-like languages that do express that kind of functionality. I'll perhaps talk about it on the last day. There's a language called P4 that's really trying to be sort of the x86 of packet processing. And there you do have the ability to look at state on the switch and make different decisions. But in OpenFlow, you can't. The switches are just there passively counting. Sorry, the counters are just there passively counting. So the question is, isn't the controller a single point of failure? So yes, if implemented naively, and if some of you maybe have read papers about software-defined networking, and often people talk about how it's so great that we can centralize all of the control plane on one machine. Of course, that's a bad idea. If that machine crashes or gets corrupted or compromised, then your whole network is basically hosed. But of course, there are standard ways of replicating data and computation. So the major production deployments of SDN in the big tech companies don't use a single controller. They use a small number of what I'm going to call tightly coupled controllers. And the reason that that's cool is that they can do things like run protocols like Paxos that give very strong consistency guarantees about the replicated data. And it wouldn't be realistic to run Paxos on every router in your data center, but it is realistic to run Paxos on maybe a dozen machines. And a dozen machines gives you a fair amount of fault tolerance. So I'm going to draw pictures that have one controller, but you should think in your mind that there's however much replication you need to get the fault tolerance and also scalability that you need. More questions?
If I somehow break my topology, does the controller lose the ability to send instructions to the switches?
Yeah, this is a good question. So the question is, if I somehow break my topology, does the controller lose the ability to talk to the switches? There's, again, naive ways to do this and more sophisticated ways to do this. So the way I've drawn it here and the way I'll draw it in all of these slides is that there's a separate control network. So there's the data network, which I'll draw with solid lines, and the control network's drawn with the dashed lines. And I'm assuming that's a basically private, reliable channel between the controller and the switches. Now, if that assumption that it's a reliable channel fails, then yes, the controller obviously can't do anything to the switches. In practice, what a lot of people do is that they don't have these two different networks. They actually use the data network as the control network. And you still have the same problem. The controller could become disconnected, but you have to then engineer your control program to be sufficient, robust to whatever failures you think are important. And I'm not really going to go into this at all in these lectures, but there's some very nice work looking at the limits of, what can you do and what can't you do in that kind of setting. And it's related to sort of classic distributed systems results. Okay. Other questions? I'm happy to take as much time as we need. I don't want people to get bored or confused because of some cartoon I've drawn that's not realistic. Okay. The controller has a bunch of instructions that can send to configure the switches. This is a subset, but it's the subset that I'll focus on today. So one thing it can do is it can reconfigure these tables. And the tables, remember, ultimately decide how packets are forwarded. And there's one message called flow mod, which is a little bit anachronistic, but it basically stands for modifying the flow table. And you can pass basically descriptions of the rules that go into that table, and then the switch will reconfigure itself. The controller can also inject packets into the network. So it does this by sort of the dual of packet in. There's a message called packet out, and it can basically craft a new packet and send it into the network. And then it can also explicitly request for statistics from a switch. So if it wants to know, right now, how much load is there on this link, it can ask the switch to tell it that. Okay, so I'm a little short on time. I'm not going to do live demos, but let me just show you some code that implements some of the devices we've seen in an OCaml system called OX that we've built. So the way that OX works is you basically, there's a runtime that I'm not going to show you, but you basically define a module that provides handlers for each of the switch to controller messages, and then it also has some primitives for sending the instructions to the switch. The runtime sort of glues all these together and gives you a controller that does the handshaking with the switches when they connect, sends the messages to your event handlers, sends the messages coming down back to the switches, and you can control a network that way. So here's a repeater, or a hub. That was the first example we saw where the device just behaves like a wire. It's a little more complicated than you might think, but let me step through it and then we can think about why it's complicated. So the first thing that we're going to do is, if we want this repeater hub to work with multiple switches, then we don't know what switches there are on the network. So we're just going to run this controller that when any switch connects to it, causes it to behave like a wire. And so what we'll do is, we'll send two messages to the switch. So first, whenever a switch is connected, we get its identifier in the message. And we can then send down these flow mod instructions. And we're going to send two. We're first going to tell it to wipe out its state. So that's the first line that says delete flow. Any stands for any pattern whatsoever. And that has the effect of just completely deleting the table. And then we'll send a second message that says add a flow. The pattern will again be any, so it'll match any packet whatsoever. And the actions, we can specify in general a list of actions. And convenient for us, there happens to be a primitive that's, it's not called flood, but it does flooding. So flood will, when any packet arrives, take the packet and send it out all of the other ports except for the one it came in on. Okay, so this does what we want. When a switch connects, we get it to behave like a hub. It turns out that we need to also define a second handler. We need to define the packet in handler. And the reason's a little bit subtle, and it's also a little bit artificial. So if you were, well, let me just say it's a little bit artificial, but it illustrates an important point. And it comes from some of the inherent concurrency in a network. So let me go back to this. So when we send these two instructions, we're doing them one after the other. And it takes some time for those messages to get down to the switch. And it also takes some time, it can take actually a lot of time, for the switch to reconfigure its internal hardware tables to implement these patterns. There have been some measurement studies where people have shown that for a kind of commodity data center switch, if it contained already a lot of rules, it can take in the order of tens of seconds to reconfigure, to basically to add new rules. Probably for these two rules we wouldn't have this, but there would still be some delays between, when this code fires and when the switch has actually been reconfigured to behave like a wire. So in the meantime, most switches, by default, if they don't have a rule in their table that matches a packet, most OpenFlow switches will be configured to send the packet to the controller as a packet in message. So we could just ignore them, but that could really confuse our users, because if the first packet in, say, a TCP connection is dropped, then you can get into the situation where you have to sort of wait for things to time out, and basically the user experience is that the thing hangs, and then the next one goes through. So if we don't want that to happen, then the controller should actually handle these packets that might sort of fall off the end of the table that we were in the middle of constructing and got sent to us. And what we can do is we can just send them back out into the network. And I'm not going to bore you with the details of how OpenFlow works, but essentially we would send the packet out and say, flood this packet too. So essentially what we're doing, I'll have some pictures of this later, is we're building up the table we want, which in this case has one rule, by wiping out the old rules and installing the rule. And then at the same time, while that reconfiguration is happening, we're letting the controller handle any packets that might fall off the table while it's being reconstructed, and we're implementing the same logic on all those packets. Okay, so that's a repeater hub in OpenFlow. Here's a learning switch. I'll step through it a little bit faster in the interest of time. So the idea in a learning switch, and again, this is a little bit artificial. You would not probably want to implement a learning switch for a large network in this way. But it's an example that a lot of people have used as kind of a litmus test for SDN systems and languages, because it involves both monitoring the network state and implementing forwarding. So the way we're going to implement the learning switch is we're going to keep the table that associates MAC addresses with ports on the controller. And we'll do this by letting the first packet in every, from every host go to the controller. We'll remember what that packet's address was and where it came from, what port it came from, in a literal hash table, in this case an OCaml hash table. And then when we know, when we see a packet where we know both its source and destination, we'll send down an instruction to install a rule so that further packets between that source and destination just stay on the switch and don't have to go to the controller. Okay, so the way I've structured this code is, first we have this hash table that stores that association, and then we have this function learn packet in that processes packet in messages that come to the controller. And what it does is it just adds the source address of the Ethernet source address to that table, and it also remembers what port the packet came in on. And then we have this more complicated routing function. So every packet that comes to the controller goes through both of these. And the routing function does two things. So first, it tries to do a lookup in the hash table. And if it finds the destination, then it constructs a pair of rules, one in each direction, one going from source to destination and one going from destination back to source. It installs those rules, sending out the appropriate ports, and then it also handles the packet that came to the controller, because the packet came to the controller because there wasn't a rule for it on the switch, so we have to handle it. So that's what this code does. And then if we don't find the destination in our hash table, then we fall through to this exception handler, and then we just send the packet out and flood it, because we don't know where it should go. And then, I think I don't have an animation for this, the overall the overall OpenFlow handler is this packet in handler that just does both of these things, learning and routing. Okay, so what this does is it basically builds up that table that I showed on my learning switch slide in OCaml, and it incrementally pushes down the rules to the switch when it's safe to do so. Questions?
So I think this is more on what further to your hub example, but are the two like send, flow mod, and structured, are those atomic? Seems like if you mash on any and erase, and then later you have a different rule, you might just like make some packets.
Yeah, so I'm coming to that right in the next. So the question was, are send flow mod instructions atomic? I'll come to that in just a sec. So let me defer that for 2 minutes. More questions?
Are all the rules you can muck around with at the packet level, or can you also screw with like media access and things like that?
Can you do deep packet inspection?
Yeah.
Yeah, so this varies. Typically, you can configure a switch to send as many bits into the packet payload as the switches have some limit. There's some point after which they can't. But if you have a switch that can send maybe the first 200 bits, that might be enough for you to get the URL if it's an HTTP request. And then it could come to the packet and you could look at it. The tables tend not, for OpenFlow, tend not to let you muck with the payload. They're restricted to headers. Some of these newer languages, this P4 language that I'll talk about in the last day, does give you the ability to basically parse, again, as long as the hardware is able to sort of, as far as it can reach. All right. So let me talk now for the last about 20 minutes about how you might reason about OpenFlow programs. And it's great that you asked the question about atomicity, and because that's exactly why this work is needed. So the motivation is, we'd like to be able to reason about the correctness of a given OpenFlow program. But I hope poring over that tedious OCaml code convinced you that even though SDN is wonderful and gives us, clean access to these programmable switches, actually the code you have to write is really subtle. You have this, event-driven program that's controlling a bunch of switches asynchronously. The switches have kind of funny semantics, as I'll show you. And, checking that the network implements some functionality is really not easy. So it involves sort of reasoning about this machine-level code, tables and what level in the table you're in, and so on. Moreover, you have to worry about sort of all possible interleavings due to the inherent concurrency in a network. And so the idea that we had was, well, if we want to ever prove anything about the behavior of one of these networks, we need some kind of calculus that captures the behavior of OpenFlow switches and controllers precisely. So just to illustrate I think the question that you had, even when you have a single controller programming a single switch, it's still a form of distributed programming. And you can't assume that your event handlers are going to kind of run atomically and instantaneously. So switches, you can't sort of stop the world and update a switch. The switch is going to be processing packets while you're sending down the flow mods. And the tables can be huge. A router might have hundreds of thousands of entries. Even a switch has sort of tens of thousands, even in a campus like here. And we have instructions that can add single entries, and you can actually delete lots of entries at once. But the instructions are kind of limited. So we can't sort of say, pause, update this table, and the switch won't do that for us. So what we need to do is somehow find ways of updating the switch while it's processing packets. And the thing we want, sorry, I haven't defined this notation, but the sort of intuitive thing we want is that the table that's on the switch, if I kind of view it as having some set of behaviors, is somehow a subset of the function that I'm trying to implement on that switch. It's okay if I don't have all the functionality in the function. So if the function is only partially defined in the table, that could be okay because the controller can handle the undefined cases. But it would be wrong if the table had behaviors that were not in the function. Okay, so let's see a simple example of what can happen. So here's a sequence of flow mods that I might like to send. And every step has that property that I just showed. So I'm trying to get down to this target. And I start out with an empty table, and I step through this sequence of tables. And what I want is that, this is a contrived example, but basically all SSH traffic is dropped, and then any non-SSH traffic that's going to host 1 and 2 goes out ports 1 and 2 respectively. What I don't want is that SSH traffic ever gets through. So if you had a kind of simple view of how flow mods get executed, you'd think, okay, well, I start out with nothing. So the default behavior is the controller handles it. Let's assume the controller does the right thing. The next step, I drop all SSH traffic. That's good. I'm not sending SSH traffic inappropriately. And then all the other tables are just filling in the destinations I can forward to. So it seems safe. But I didn't tell you this, but switches are actually allowed to reorder the messages that they get from the controller. So it's not just that an individual flow mod may or may not be atomic. Typically it is. The bigger problem is if I send down several of these flow mods, the switch might decide, well, my table is kind of already set up to make this third instruction you sent easy. I'll do that one first. And so what I can end up with is I could step through this series of tables. So here, traffic gets forwarded to host 1, and then to host 2, and then finally I install the rule that drops SSH. And this, of course, is wrong. Right? In the interim between these two, I'm improperly I'm allowing SSH traffic to go through. So if you show this to networking people, sometimes they say, who cares? Transient policy deviations or failures are often acceptable. I have an apocryphal story that I did not witness, but a friend who worked at this company told me this very large ISP used to update their firewalls periodically, and they did it essentially like the incorrect path here. They would uninstall all of the access control lists and then just lay them down one by one, and hope that that happened really fast so that no attackers could get in. So that, if you're a PL person, that's kind of drives you nuts. And if you're a person who uses things like cloud data centers, that should also drive you nuts because one of the properties that you want is you want to be isolated from other possibly malicious users of the network. And so you're really unhappy if even for some transient period, maybe a few milliseconds, maybe a few seconds, if someone can send packets through that they shouldn't, there's some significant danger that they could do something really bad. So we would like to not have this happen. So how can we do it? Well, I didn't tell you this, but OpenFlow also has a kind of synchronization operation called a barrier. And what a barrier, the semantics of a barrier is that if a switch receives a barrier instruction, it is not allowed to proceed past that barrier instruction until it's processed all of the instructions that it received from the controller previously. So between barriers, the switch can reorder the control messages however it likes, but it can't go past the barrier until it's kind of flushed its buffer of messages.
Sorry, I was thinking of the question, just maybe gave the answer. So does it drop incoming packets?
packets, or does it keep them in a queue?
So it's going to keep processing packets. That's allowed. But what it's not going to do, so the bad thing that happened here was, the bad thing that happened here is we sent down these 3 control messages in this order, and the switch decided to do them in some opposite order. So the way we could do it with a barrier is we would send down the first one and then say barrier. And now the switch is not allowed to do the second 2 until it's already updated the SSH rule. So we know that we're in this state, and then we probably don't care which of these 2 rules gets installed first. They can happen in any order, but we would definitely need a barrier right here.
Maybe I missed something, but then messages can't be reordered on the network.
So the connection between the controller and the switches is in order. So the controller can send a queue of messages, and that order is preserved. But then when the switch pulls them off, they can reorder them, except over barriers. OK, so if you want to prove anything about an OpenFlow network, a controller and some switches, you need to reason about these kind of low-level properties. And like a lot of languages not developed by people who came to OPLSS, the OpenFlow spec is not some operational model or denotational model. It's a bunch of English prose. It's got some diagrams and flowcharts. It's got some C-struct definitions. It has some, when you read one of these informal specs, you can always tell when they're trying to be careful in something subtle because they use words like shall and they sort of, say things really emphatically. But there's no real definition of what these behaviors should mean. So, if you want to do a proof, it's really not sufficient. So what we did in Featherweight OpenFlow is we took a subset of the specification document. We, for pragmatic reasons, did not. Do people know Peter Sewell? Peter Sewell is a researcher at Cambridge. He specializes in doing this kind of exercise, but he doesn't cut any corners. He takes the whole the whole shebang and formalizes it in full detail. So we didn't do that. We did take all of the features in the spec that are related to packet forwarding and all of the possible sources of concurrency or asynchrony. So we made sure that our model was faithful to our best interpretation of the English prose specification on that subset. We didn't model statistics. We didn't model various error conditions, like what happens if a malformed message comes, what happens if a switch doesn't obey the handshake. We ignored all that stuff. I believe you could extend this with all of that, but it would add a lot of clutter in directions that were not interesting to us at the time. OK, so I want to show you in some detail how this operational model works. I was not here during the first few days, so I assume everyone has seen operational semantics. And I saw a Piazza post about concurrency. I don't know were all the semantics that you saw deterministic? Yeah. Small step deterministic. OK. So it turns out operational semantics is nice because it's very simple and flexible. So we'll be able to use the same kinds of techniques to model this kind of highly concurrent system. But the details will be a little bit different. And as inspiration, we're going to start from something that is called the chemical abstract machine. This is it's a machine, but in common use today, it's sort of a general technique for modeling concurrent systems that was developed by Berry and Budal in the late 80s. I think the paper is Popple 90. So the idea is that, unlike, say, a small step semantics for a C-like language or lambda calculus, where you have sort of the configuration of the system, and then you take these steps, either big steps or small steps, often deterministically. In these concurrent systems, you just have sort of a bunch of stuff. Let me call them processes. And so these processes, or even molecules, are sort of in this solution or soup. And sometimes 2 processes will sort of come together and interact. And so we'll have rules that tell us sort of when 2 molecules can come together and interact, and they'll together step to some different molecules. They might consume some of the molecules, they might produce new molecules, they might change their state. And so the overall semantics is highly non-deterministic. We just sort of define all the rules and then start out with a bunch of our initial molecules and sort of let the system go and see what happens. OK, so what does this look like in the context of OpenFlow? So for Featherweight OpenFlow, we had, I believe, 4 kinds of molecules. Essentially, we had sort of 1 for each of the components of our system. So the switches, And I apologize, my fancy hollow font, which follows what we did in the paper, is kind of hard to see. Is that S legible? Okay, so the switches are this molecule, and they have a bunch of internal states. So they have some unique identifier. They have their current flow table, which for the purposes of this lecture, I'm not going to go into the details about how flow tables are represented. You can see our paper if you want that detail. But just think that there's some data structure that represents a table. And then they have input and output buffers. So packets that arrive at the switch go into these buffers. And the buffers concretely are multisets or bags. So the same packet can be there multiple times. And there's no particular order associated with the packets in those buffers. And then they also have a buffer of control messages. And these are messages that the switch has sort of generated that it wants to send to the controller, but hasn't sort of gotten off the switch yet. So that's the switch molecule. We also have molecules for the data links in the network. And these are indicated by a molecule whose name is L. So a data link has a source and a target. It connects two particular switches at some particular ports. So we have on the left side SW and PT, and on the right side SW prime and PT prime. And then a link has a bunch of packets, and most links most physical media that are used to implement links preserve ordering. So here, unlike the buffers on the switch, the PKTS is actually a list of packets that have been sort of enqueued on the link. Okay, we also have a controller molecule. And I should say we tried to do this work very generally. We weren't trying to prove our controller correct, so we tried to come up with a model that could be instantiated with lots of different kinds of controllers. So the controller has some internal state, sigma. It has a function fin, which is basically the event handler. So the fin takes OpenFlow messages that come from the switches, and then it can produce one or more output messages, one or more output packets, and also some output messages. And then it also has what we call an output function. And this is a function that can sort of fire whenever it wants. So the reason we needed this second function was that in addition to sort of being event-driven, controllers can also have things like timers. They can just decide, once a minute, I'm going to do something. And so that fout lets us model that. Okay, and then we also have the separate control links, which contains, again, a bag of control messages. Okay, so I haven't told you what the OpenFlow messages are precisely, but I guess you saw them on an earlier slide. So the messages are basically flow mod with either add or delete for elements of the table. And then barriers, we have requests and replies, and then packet in and packet out. And I'm not going to be too careful about this, but you can actually separate all the messages into messages that go only from switches to controllers and messages that only go from controllers to switches. Switches never send a flow mod, for example, only the controller does. Okay, so to model a network, what we do is assuming a single centralized controller, we pick one controller molecule that's running the function fin and fout that we want. We pick one M module, that was the controller links. So the one M module represents all of the links between switches and controllers. The decision to have one M molecule is a little bit debatable. You could have multiple M molecules if you want. It was slightly simpler for us to just have one. And then one S molecule per switch and one L molecule per data link. And then the overall sort of network model is the concurrent composition written with a bar of all of these molecules.
What it means you have more than one M molecule?
So in what I'm going to show you, there is not. So it would be incorrect. It would not be well formed. It would not be a well formed system to have multiple M molecules. You could choose to have multiple M molecules, and the bookkeeping is just a little different. So that's for our paper, we chose to just have one M molecule and to have all the messages coming up to the controller be non-deterministically multiplexed onto that M molecule. It's just a choice of modeling. Okay, so let me show you the operational rules that govern how this system. Oh.
Yeah, I was just wondering if the messages arrive distributed order, why are we not switching to
So the question is, if the messages arrive to switches in order, why don't switches process them in order? I'm not sure I can give the answer to that question with any authority. I think there's two reasons. So the getting a standard like OpenFlow to be sort of accepted by a bunch of hardware vendors was this amazing feat of social engineering that the people behind SDN pulled off. And to do this, they had to basically convince all these hardware vendors that, exposing this general API and letting other people write software for your box is not going to eat your market share, and we're not going to somehow change the standard and force you to change how you build your hardware. So they tried to write the spec as loosely as possible. And I think that's one reason. And then in the wild, some switches do, for various reasons that I don't have any deep knowledge into, do reorder messages. Do switches reorder, are all interleavings exhibited by some switch in the wild? I don't know. I do know that they will do things like adds and deletes they'll reorder because, okay, I don't want to go too deep into this, but these tables are very complicated circuits, and the tables have to have the rules in order because that's how you sort of match starting at the top and going down. And if you want to express certain conditions like negation, you need to basically negate what you don't want and then fall through to what you do want. So the circuits that implement the table can be sort of densely packed into sort of levels. And then if a control message comes and says, please insert something in between two levels and there's no sort of space in the circuit, then the switch has to do a kind of internal garbage collection or internal rearrangement to move other rules down to make room. So there are kind of these really heavyweight operations, and for whatever reason, some vendors choose to sort of do the cheap work before the expensive work. Yeah, I think that's all I can say. More questions?
We use barriers to avoid the problem of ordering, but doesn't barrier itself decrease the performance?
Yeah, so it would be, if you sent a barrier message between every single control message, first of all, there's extra overhead for the switch to process that message, and you're sequentializing things, which will make things slower.
Secondly, each packet itself, if it's in the form of flips or something, it has a sequence numbering. Why do you require an additional sort of barrier to order? There must be a number associated with each packet. That number can be used in the destination to order on the packet.
So the question is, packets have a sequence number, why do we need barriers? So one thing that's important to recognize is that there's two different kinds of packets. There's the control messages and there's the data packets. So the barriers do not affect data packets. Okay, that's an important point that many people miss. Packets are still, the data plane is still processing packets. The switch's local logic is choosing to basically interpret the control messages when it can. So that's one clarification. I guess the second point is you could use the sequence numbers that are carried by packets, but and actually OpenFlow itself has a kind of sequence number, something called a transaction ID that you could, if the controller were to increment it reliably, you could rely on. I think it would be a little dangerous to assume that the sequence numbers are always monotonically increasing, because the connection between the switch and controller could break, it could reset, then the sequence number would potentially be reset. So you have to be a little careful relying on artifacts from TCP and how you design your control protocol. So barriers are a simple way to sort of give yourself that power to synchronize without relying on anything from the underlying transport. More questions? No. Okay, great. So we can talk about the actual rules. So the first rule is sort of the main, I don't know if you guys talked about congruence rules, but this is an abstract rule that says whenever I have my soup of processes, and there are a bunch of processes composed in parallel, I can pick off one of them. So I'll kind of write my process as sys1, which is part of my system composed in parallel with sys2. If I let sys1 step, then the whole thing can step to whatever sys1 steps to, and the sys2 part gets carried along. Okay, so the intuition is, if any sub-collection of molecules in the system can react with each other, then the system can allow that reaction to happen. Now, you might wonder, have I really captured that here? And there's another important rule that lets us sort of rearrange the syntactic presentation of our molecules so that this rule can fire. And This is sometimes called structural congruence. There's many ways to formalize this. This is one of them that's commonly used in the research on concurrent process algebras. So the idea is we're going to define a second relation, which I've shown with a triple equivalence symbol. And it just says that parallel composition is commutative, so it doesn't matter which order you write the left and right sides, and associative. So it doesn't matter where we put the parentheses. You can always rearrange them any way you like. And then we have another reduction rule that says, if I haven't screwed up my primes, I think I haven't, if you can take this process you start with, system 1, and rewrite it into system 1 prime, and then let system 1 prime step to system 2 prime, and then rewrite that into system 2, then system 1 can step to system 2. So this rule basically lets us use this congruence anywhere in any reduction that we want. And I didn't say this and I didn't write it, but this triple bar equivalence would also be a congruence. So there would be rules that say that you can apply this rearranging deep under other things that we might have in general. In our setting, we don't need it, but in general, you'd have other rules. Okay, so all this does is just basically says that concurrent composition is both associative and commutative. Okay, then we get to the actual reaction rules that do some work. And I have about 10 of these. They're a little bit fiddly and complicated, but this is where sort of the rubber meets the road and all these choices about where do we have concurrency or where we don't and where can we rely on orderings come up. So the first rule talks about what happens when a switch receives a packet. So a packet is parked on some data link in its queue, and it's the head packet in that queue, and the switch grabs it and pulls it into its internal buffer. And that's exactly what this says. So basically a link molecule and a switch molecule can come together. The link molecule has to be adjacent to the switch at this port, and we can pluck off that packet, which is written using ML-style list append at the end of the queue, and we can pull it into our input buffer. So we transition to a link molecule where the packet's not in the queue, and we stick the packet into our buffer. Okay, so this just captures switches pulling packets off the wire and then putting them into some unordered collection. And I'm not going to be too careful with notation, so if you have questions, ask, but essentially I'll try to use sort of set-ish notation for sets and bags and list-ish notation for things that are ordered. Okay, so once a packet's on a switch, the next thing you might want to do is to process it. And the processing for a given packet is governed by whatever table is on that switch. You can formalize this in more detail. I'm going to cut it off today to avoid going further, but let me assume that I have some way of interpreting a table data structure as a function that takes a packet and gives me some output packets and possibly some output control messages. Those output control messages would be packeted messages. So that's what the funny hollow brackets, stretchy brackets mean. I could formalize that, but I'm just going to assume that I have that function already. So now a switch processes a packet by pulling some packet out of its input buffer, running it through its table, yielding some output packets and some output messages, and then it just sticks those output packets into its output buffer and the output messages into its output message buffer. So nothing's really happened yet. The switch hasn't actually forwarded anything, but it sort of computed some stuff that will be forwarded and control messages that will be sent in the future.
If your in buffer is a set-ish type thing, is this how you deal with duplicate types?
Sorry, I should say multi-set. Sorry, the input buffer is a bag. Yeah, yeah. I'm not these slides. I didn't want to clutter. There's no good notation for bags. I didn't want to clutter it up with like some heavyweight notation for bags. So pretend they're bags. Okay, so that's how forwarding works. And then to sort of finish a processing step, sort of the dual of switch ingress is switch egress. So we can take a packet that's in an output buffer and stick it out on the adjacent wire. So that's what this rule does. And it puts the packet at the front of the queue on that wire. Okay, so that's the kind of data plane functionality, pretty simple. And then the control plane functionality comes from some reaction rules that talk about how switches process control messages, and then some that talk about how controllers interact with the control network. So the first and I think most intuitive is adding a rule to the table. And as with the table function, I'm going to assume that we have sort of some way of interpreting these instructions to give us functions that take some old table and give us a new table. They manipulate the table, but I'll just model them functionally. So if the switch has a flow mod that adds a rule with priority n, so at level n in the table, and some pattern and some actions, then we can take our current table, run it through that addition, we get some new table t prime, and that becomes the table that the switch uses from now on. And so this captures what you had asked earlier, which is here flow mods are atomic for a single rule. Okay, delete is entirely similar. We take a delete message that's sitting, a flow mod delete that's sitting in our buffer. We manipulate the table and update the table on the switch. Okay, the next control message that we could have is a packet out message. So if the controller has sent us a packet that should be output, that packet gets stored in our message buffer. And at some time, the switch can decide to take the packet that's sort of stored in its message buffer, encapsulate that message, and stick it in its output buffer. Okay. So those are the sort of internal switch rearrangements that happen when we process control messages. And then there's a third set of messages that govern the actual switch to controller and controller to switch interactions. So for switch to controller, what we can do is if the switch has some outgoing message in its buffer, then we can basically just add it to the M molecule that captures all of the messages coming from any switch. And we keep the messages from a switch in order on that wire. Of course, the switch may have rearranged them internally in its own buffer. Okay, and then the interesting case has to do with barriers. So if we have a message that's been put on the message on the M molecule wire from the controller going to this switch, and if that message is not barrier request, then we can step to a new configuration where the switch has pulled that message into its message buffer. So if it is barrier request, we can do something else, but if it's not, we can just add it. If it is barrier request, so here the message that's in the message molecule is a barrier, then the switch has to have an empty message buffer before it can pull it in. And what happens is, atomically, the barrier request gets consumed, and the switch immediately puts a barrier reply in its message buffer, in its outgoing message buffer. And that would eventually be sent to the controller. Okay, so that's how we model the controller to switch messages, including barriers. And then the last two rules are for controllers. So the way the event handler works is if the controller has a message on the buffer, then it can run its input handler, and it updates its state. That's it. And then it can also run its output handler whenever it wants, which produces some more packets and potentially some more outputs. Okay, so I want to finish up in about a minute or two. So the end went a little bit quick. I'll put these slides on the Piazza or on the website so you can see them. You can also see our paper where they're defined in full gory detail. Just want to also mention that one thing that we did in this work was we wanted to have a really high level of assurance about the correctness of our implementation. So we actually implemented this model and an accompanying controller for SDNs on top of it. And you can find that on our GitHub page under the Featherweight OpenFlow repository. So there's a executable cock model of Featherweight OpenFlow. Okay. So to wrap up, I want to say a few things about how you might use this model. And the way that we thought about it, this isn't the only way you can think about it, but the thing we were most interested in was we had a high-level language for describing packet processing functions. And we wanted to implement this on an SDN controller. And so what we wanted to know was that somehow our implementation was correct. But there's a kind of mismatch between our language's view of a network and the SDN's view of the network. So our language's view of the network was and you'll see the language tomorrow, is this purely functional language for describing packet processing functions. So if you sort of run a packet through a program in this language, you get a trace that captures sort of where the packet went and what values it had at every hop. Meanwhile, in the network, you have all this asynchrony and flow mods and barriers and queues and buffers and so on. And so down there, the traces that you would get from that system are way more complicated. So how are we going to relate these? So to show it with pictures, we're interested in settings where you have some functionality you want to implement, and let's assume it can be expressed as a sort of series of traces, like this. And we have an OpenFlow implementation we want to relate these to. I don't have a whole lot of time to go into this, but in general, the kinds of equivalents that you use in simple sequential systems don't really suffice. They either don't capture the notion of equivalence you want, or the proof techniques aren't good enough to be able to establish these equivalences. So simple trace equivalences won't work. And so what we did instead was to appeal to a theory that was developed in the context of process calculi called bisimulation that lets us relate these two kinds of systems. And I'll just mention this. So I assume that probably half of you have seen bisimulation and half of you have not. So I thought I'd just sort of mention it and illustrate it. So for those of you who haven't seen this, maybe the next time you see it, you'll know what it is. And if you have seen it, then you understand in more detail what I'm showing, and you can read our paper and see what's going on. So the idea in bisimulation, and we're using a variant called weak bisimulation, is we take the two systems that we're trying to relate, and we separate the kinds of transitions they can take, and in particular the kind of observations we can make on those transitions, into some that are sort of observable, and I'll use alphas to range over those. So think of like a packet being processed at a given switch, from internal actions that are sort of private to one of the systems or the other. So in our setting, we chose packets being processed at a particular device as being the observable locations that we wanted to reason about, and everything else was internal. So all of the transitions that the featherweight OpenFlow model might take to move packets in and out of buffers or do some internal rearrangement of the table, all of that would all be an internal action. And in a weak bisimulation, what we want is that if we have, say, maybe our simple functional description of a network, let me call it a process P, and then we have a complicated implementation Q, we want that if these things are related by a weak bisimulation, then whenever P can take one of its observable transitions, like a packet being processed at a particular place, then, and I see my animation messed up, I'm sorry, then there exists a bunch of steps that the implementation can take, but the implementation has to basically do any number of internal transitions, then match the observable transition that the upstairs took, and then it can do a bunch more internal transitions. And it has to leave us in final states P prime and Q triple prime that are related. So by the way, this is not the definition of weak bisimulation, but this is an instance of one of the conditions of weak bisimulation. It's the one that we're going to use. Okay, so to draw it in a little more detail, in our high-level view, packets sort of flow across the network, going from one host to some other host across a series of switches, and they might assume a series of intermediate values because the packet might be modified at intermediate hops. And then downstairs, we could have much more complicated behavior. So the packet starts at the host, it goes to the switch, maybe the switch doesn't have the full table to implement the function, so the controller gets involved, it sends and removes some rules. That can happen multiple times. But we can actually define a relation that satisfies this condition of being a weak bisimulation that relates all of the states of these things, well, in particular the starting and stopping. Moreover, we actually did this all in Coq. So I apologize for doing something a little bit in cartoon style, but if you want to understand this in a little more detail, you can look at any number of lecture notes on languages like PyCalculus or CCS or CSP, and you can also read our PLDI paper, which I have a reference to at the end. We actually proved that you can get this kind of weak bisimulation for any OpenFlow implementation that satisfies two properties. And we divided these into some safety properties and some liveness properties. So the safety properties are what I said before. At all times, the rules on the switches need to be, let me wave my hands, a subset of the controller function. So if there's ever a discrepancy between the controller function that we're trying to implement and the rules on the switch, then the switch might do the wrong thing. Right? It might receive a packet and have the wrong behavior. So we need that to not be the case. And then we also need that because the rules are a subset, if packets get diverted to the controller, then the controller can't hold on to them forever. It has to eventually process the packet according to the high-level function. And it does that by sending a packet out message. So what we showed was that for any controller that satisfies these two properties, you can get a weak bisimulation between the abstract sort of high-level function and the concrete implementation in OpenFlow. And we actually built the version of the frenetic SDN controller that is a fully functional usable system from this COC implementation. And we've since diverged from that, but circa 2012, 2013, our implementation was actually extracted from the code that satisfied this theorem and had been proved correct. Okay, so let me wrap up because I think it's almost lunchtime. So conclusion, I hope I've convinced you that network systems are important and also mathematically fun to play with. We did a bunch of networking basics. We looked at SDN, and we looked at this featherweight OpenFlow model, which is our machine model of these programmable switches, and we talked a little bit about bisimulation. As reading, if you want to do a little more reading, I just highlighted 3 articles that are all pretty high level and short, with the exception of the last one. So you can read the original paper on OpenFlow. It's a short paper in the SIGCOMM CCR. It sort of spells out the rationale for why SDN and OpenFlow make sense. You can also read a survey article that Martin Casado and Arjun Guha and I wrote a couple years ago for CACM that spells out some of the, again, this is written for a general audience, not a PL audience, so high-level motivation. And then the technical piece of today's lecture was from a PLDI paper from 2013. Let me briefly acknowledge my collaborators, Martin, Arjun, who actually did most of the work on the COC implementation, and Mark. And just to preview tomorrow, we're going to levitate ourselves out of this machine level stuff and look at this language called netcat, which is based on clean algebra. All right, thanks.